I'm going to talk about correlation matrices, why the matrices we encounter in practice might not be true correlation matrices, and what we can do to fix that. If you'd like to get the slides, there's a link there, the URL from which you can download them. So let me first of all give the usual statistical definition of a correlation matrix. We have these n vectors x1 to xn, each is an m vector, and they're samples of some random variables, and from those we can form a covariance matrix. And then by scaling the diagonal to have unit diagonal, ones on the diagonal, we get the corresponding correlation matrix, whose elements Cij are the correlations between the individual variables. So that's the statistical way of looking at things, but I want to take just a purely mathematical approach to define a correlation matrix. So it's just a symmetric matrix that's got ones on the diagonal and all of whose eigenvalues are non-negative. So what can we say about such a matrix? Well, there's one useful fact we can immediately deduce, because for any positive semi-definite matrix we have this inequality here, that the ij element is bounded above by the square root of the product of the corresponding diagonal entries, aii and ajj. Since the diagonal is 1 for a correlation matrix, we know that all the elements off the diagonal are bounded by 1, which of course is natural for correlations. So let's just start looking at a very simple example of a potential correlation matrix. This is a matrix depending on one parameter w, and I want to ask for what values of w is that matrix a correlation matrix. You might be tempted to think that any w between -1 and 1 would work, but in fact w has to be at least -0.5, and it can go all the way up to 1. So the range of w that make a correlation matrix is not symmetric about the origin. In general, for an n by n version of this matrix, the condition is that w is between -1 over n minus 1 and 1. Now, a question that naturally arises is, what are the possible eigenvalues of a correlation matrix? We know that they have to be non-negative because we have a positive semi-definite matrix. The trace of a correlation matrix is clearly n, that's the sum of the diagonal entries, and we know that the trace of a matrix is also the sum of the eigenvalues. So we know that the sum of the eigenvalues must equal n. So the eigenvalues have to be non-negative and they have to add up to n. But are there any further constraints? Well, here's a theorem that will help us answer that. It's a well-known theorem from matrix theory, the Schur-Horn theorem. And it talks about a symmetric matrix with given eigenvalues arranged in increasing order and given diagonal entries arranged in increasing order. Now in our case we want to take all these alphas equal to 1. And the final one of these n inequalities just says that the sum of the eigenvalues equals the sum of the diagonal, and both sides are equal to the trace. So that's an equality, as is stated in the theorem, and we already know that. But what's new is that for k is 1, the smallest eigenvalue must be bounded above by the smallest diagonal entry. The sum of the first two smallest eigenvalues bounded above by the sum of the first two smallest diagonal entries, and so on. So these are called majorization inequalities. And if you think about it for a bit, you'll see that in fact these don't impose any further conditions on the eigenvalues. So any set of non-negative entries summing to n can be eigenvalues of a correlation matrix. So I just want to show you some examples. And sometimes in practice we want to do simulations where we generate correlation matrices with given eigenvalues. And there is an algorithm for doing this by Bendel and Mickey, which you can think of as being inspired by that theorem. And I did some work on this with Davis, and we managed to improve the algorithm in a couple of ways. This algorithm is now built into MATLAB. It's gallery rand core, so you just give it the vector of eigenvalues that you would like here. So let's try 1, 1, 1. So we expect to get a 3 by 3 matrix with eigenvalues 1, 1, and 1, and it should be a correlation matrix. So here's what comes out. A modulo round-off, we've got the identity matrix here. And indeed, that's what you'd expect. The only correlation matrix with eigenvalues all equal to 1 is the identity. Another special case would be to set the eigenvalues to 3, 0, 0. Again, they add up to 3, so these are allowed. So this is going to be a rank 1 matrix because it's only got one non-zero eigenvalue. And as such, it has to be the matrix of all ones. So again, that's a rather special case that's not very interesting. More interesting is 2, 1, 0 as the eigenvalues. In this case, we get a genuine non-trivial matrix. And I've just checked here that the eigenvalues are indeed within round off what I requested. Okay, so there's a couple of problems I want to talk about, and the first one is illustrated by this example here, a 3 by 3 matrix, and let's suppose we're not sure about the 1-3 entry. Let's just try setting it to 0 and see what happens. So there's a matrix that may or may not be a correlation matrix. Let's check if it is by computing its eigenvalues. Well, it has a negative eigenvalue, minus 0.2728, so this is not actually a correlation matrix. So the first problem I want to look at is, given that matrix, can we perturb it to make it a correlation matrix? So can we find a small perturbation, as small as possible, to produce a true correlation matrix? We want to keep the ones on the diagonal, but we want the eigenvalues to be non-negative. The second problem is at first sight a bit similar, but now we're going to say, what are all the possible thetas we can put in that place if we don't know this entry in order to get a correlation matrix? And then how do we choose amongst those thetas? So this is a completion problem now. Now in this case, I can plot the smallest eigenvalue as a function of theta, with theta going between minus 1 and 1. And we'll see that once theta gets to about 0.62, the smallest eigenvalue becomes non-negative. So there's an interval of possible thetas here, any of which will give us a correlation matrix. So where I first came across these types of problems was some contact with a London fund management company about 20 years ago. And they told me they had some symmetric matrices arriving from stock data, and they should have been correlation matrices but were not. And so they wanted to perturb them to make them correlation matrices, and they wanted the minimum Frobenius norm perturbation. They asked if this perturbation was unique and how we could efficiently compute it. And they were dealing with matrices of the order somewhat over 1,000, and these matrices were going to be growing over time. So computation time was an issue here. Over the years, I've had a number of emails from people working in the finance industry with similar sorts of problem, essentially the same problem or with some variations. But in every case, there's a matrix that for some reason or another has not turned out to be semi-definite, and they want to perturb it to make it a true correlation matrix. So what is the underlying cause of these problems then, of the lack of definiteness? Well, there are several possible reasons. One is missing observations. So your underlying data may just have some gaps. For example, if this is stock data, there may be companies that were formed during a period, but you don't have data for the company at the start of the period, or if the company is closed at the end of the period. You might have asynchronous data. If you're looking at markets that operate in different times around the world, that can cause problems with the informing the correlation matrix. And another one is stress testing, whereby you sort of artificially impose certain values on elements in the matrix, and in doing so you may destroy the property of it being now a true correlation matrix. And what's the problem of having a negative eigenvalue? Well, a lot of the things that we take for granted are no longer true anymore, and strange things can happen. So for example, in portfolio management, you can get a portfolio with negative risk, something that is impossible. So the question is then, how do we make this given matrix semi-definite again? So simple-minded idea might be, well, the problem is a negative eigenvalue, so let's just shift the eigenvalues up by adding alpha times the identity to the matrix. And if we choose alpha big enough, that will certainly make all the eigenvalues positive. It will also, though, change the diagonal. So we will now have 1 plus alphas on the diagonal, and so we need to divide by 1 plus alpha in order to get a unit diagonal again. In general, if you had a non-unit diagonal, you could, in general, do this diagonal scaling where d is the diagonal of A to reinstate the unit diagonal. But that's not a good approach, really, because it's rather ad hoc, and it won't be the optimal perturbation at all. Another approach would be to go back to where the data came from, and in the case where you have missing data, just fill in the gaps. And there are various statistical ways of doing this, so that's a perfectly sensible thing to do. Although the company I initially spoke to didn't want to do this, they wanted to perturb the matrix that they've constructed. So let's now focus on that, on optimally perturbing the matrix to produce a correlation matrix. So here's the problem. I'm using the Frobenius norm. So the Frobenius norm of a matrix squared is the sum of the squares of the elements in the matrix. and I want to find, given an arbitrary symmetric matrix A, what's the nearest correlation matrix to A, the nearest C. So the constraints here are characterized, so a correlation matrix is at the intersection of these two sets. S is the set of positive semi-definite matrices, symmetric and positive semi-definite, i.e. non-negative eigenvalues, and U is the matrices that are symmetric with ones on the diagonal. And so the correlation matrix is at the intersection of these two sets. And that intersection is a convex set. It's a closed set. And so you can conclude from existing approximation theory that there is, in fact, a unique solution to the problem. Now, when I first came to look at this, it turned out that looking through the literature, various methods have been proposed over the years, all rather ad hoc, in the sense that they weren't guaranteed to solve the problem. They were iterative, usually, and so might not converge or might converge to something that's not an optimal solution. So I looked at this, I developed some theory and an algorithm. And I just want to briefly give you the feel for the algorithm I developed via really a simple diagram. Now what I'm going to use here is an idea that goes back to von Neumann. So von Neumann was looking at finding points in the intersection of subspaces. So in this diagram here, we've got two subspaces, S1 and S2. We start at this point here, and we want to find, we want to move to the intersection of S1 and S2. So von Neumann's idea was you first project onto S1, and projection means has this notion of orthogonality, so we're hitting S1 at a right angle. Then we project onto S2, so we've now lost the property of being in S1, but we now have the property of being in S2. But if we go to S1 again, then S2, you can see we should be zigzagging in to a point that's in both sets, in that intersection. So in a sense, proof by picture, it looks like this algorithm should work, but of course this actually needs careful mathematical proof. And there's one slight problem here, which is one of my sets is a subspace, but the other is a convex set. And Dykstra derived a correction that allows this algorithm to work when you have a closed convex set. So this approach is very easy to implement. It is guaranteed to converge. That's the good news, although the convergence can be rather slow because it's only linear. And if you have linear convergence with constant 0.999, then that can be very slow convergence. A very nice feature of this method is that you can add further constraint sets. So if, for example, I want to keep fixed a certain part of my matrix, let's say a certain submatrix, I can just add that as a further set. And then the projection onto that set just becomes, reset those elements to the values you want. So it's a very versatile algorithm, the alternating projections algorithm. However, another method was developed a few years later by Chi and Sun, and it's a Newton method. And in general, if you have a nonlinear equation to solve or a nonlinear optimization problem to solve, and if you can construct and actually implement a Newton method, that's generally a very good thing to do, as long as you can get it to converge. Now, in this case, Chi and Sun realized that the best way of approaching this was to apply Newton to the dual of the problem. The original problem has constraints, as we've just seen. The dual problem turns out to be unconstrained. But the dual problem is not differentiable, unfortunately. So at first sight, it doesn't look like you could apply Newton's method to the dual problem. However, Chi and Sun are experts in semi-smooth optimization, and they were able to show that you can in fact apply Newton, and that in fact it's globally convergent, and as Newton usually is, quadratically convergent. So this promises to be a very good method. I looked at this with one of my PhD students, Rudiger Borsdorf, and we came up with one or two improvements to the implementation and efficiency. And this algorithm was then implemented in the NAG library as GO2AA. And there's a link here to more information about that. So I want to show you just a little example in a moment of how those algorithms behave. But before doing that, just let me point out an interesting property of the nearest correlation matrix. And it's in this theorem here that if the original matrix has t non-positive eigenvalues, then the nearest correlation matrix has at least t zero eigenvalues. Now, intuitively, the reason for this is that we start off with our A, let's say, with t negative eigenvalues. We want to perturb those eigenvalues to be at least zero. So we've got to move them to the right along the real axis to make them at least non-negative. And since we're making the minimum possible perturbation, there's no point moving those eigenvalues any further than the origin, otherwise we'd be doing more work than necessary. So intuitively, this result makes sense for that reason. Here's a matrix of some real stock data that I'll just show you the eigenvalue distribution for. So these are the moduli of the eigenvalues. So there's a number of eigenvalues around 1 in modulus, and then there's a lot of really tiny eigenvalues. And in fact, most of these are negative. So this matrix has 1,245 non-positive eigenvalues. So most eigenvalues are non-positive. And so by the result I've just described, the nearest correlation matrix will have very low rank, just 154 at most. And for this matrix, the distance to the nearest correlation matrix turns out to be just under 21. So I'll use that matrix on this slide here, where I'm going to contrast the speed of the Newton method with the alternating projections method. So I'm going to use my MATLAB implementation of alternating projections and the NAG library implementation of the Newton method. I've got a couple of random problems, dimensions 100 and 500. I'm solving those fairly accurately with tolerance 10 to the minus 10, and for this bigger matrix, tolerance 10 to the minus 4. This is a much harder problem. And what you can see is that the Newton method is quite a bit faster than the alternating projections, especially for the larger problem. And the number of iterations required by Newton is pretty much constant here, whereas alternating projections, being linearly convergent, is requiring more work as we get to the more difficult problems. So generally, the Newton is to be preferred. It's faster if you have software for this. But the alternating projections does have the advantage that you can easily add in further projections to the method. Now, in the course of doing all this work, I've collected a number of real-life matrices that have this property of not being actual correlation matrices, but were supposed to be. And I've made this available on GitHub, so you're welcome to go there and download these matrices if you'd like to try them. Just a few highlights. There's a 3250 matrix of EU bank data, a very small matrix from portfolio risk, another stock data matrix of dimension over 3000. So the sizes vary tremendously here. Stress testing, foreign exchange trading, stress testing, and this last one is carbon dioxide storage resources. So all of these were from financial problems except the last one. So why have we got a non-finance problem here? Well, it turns out that this nearest correlation problem is actually very widespread nowadays. And using Google Scholar, I can see which papers are citing my original 2002 paper on this problem. And looking through that list, I found a real huge variety of problems where of applications where this problem arises. So we've got a modelling of German winter storms here. We've got breeding of horses, cartridge cases from guns. We've got 20th century sea levels, and tourism in Copenhagen. So what's happened is that this problem, while I think originally, as far as I'm aware, it only seemed to appear in finance problems. With the growth of big data and the growth of data science, it seems that in applications where you have large amounts of data, you're very likely to have this same problem of a computed correlation matrix not being a true correlation matrix, and then you want to perturb it. So it's really a very widespread problem nowadays. The second variation of the problem is the completion problem. So this is where we have some unknown elements in the correlation matrix and we want to fill them in. And I'll describe a little example here with respect to risk management. So imagine that we have two business units, B1 and BU2. So BU1 is exposed to 3 risks, X, Y, and Z. BU2 just to 2 of the risks, X and Y. And we know all the correlations except the correlations between X and Y in business unit 1 and Z in business unit, X and Y in business unit 2 and Z in business unit 1. In practice, in the worlds of insurance, these correlations are often actually set by humans using expert judgment. And so this could correspond to a situation where there is nobody who understands both BU1 and BU2. They could, for example, be operating in different parts of the world. So we have these unknown entries in green, these 2 numbers here, same as these 2 by symmetry, that we want to fill in. Now, in general, of course, there might not be any possible choices of those numbers that will give a correlation matrix. It all depends on the structure of the problem. And there are some conditions that are known to guarantee that there will be a completion. The usual one is that the structure of the matrix, of the graph of the matrix, is caudal. So you have a caudal graph associated with the matrix. I won't define caudal here, but that is something that can be checked. So I'm just going to assume that there is a completion. Now in general, if there's one completion, there'll be infinitely many, and so the question is, which one should we go for? Well, the usual answer here is the maximal determinant completion. So of all the possible completions, we want the one that has the largest determinant. And it turns out this completion is unique if completions exist. And it has some very nice properties. So it has this maximum entropy property, it has a maximum likelihood property, it turns out to be the analytic center of the feasible region, i.e. the set of all possible completions. And then the last one's a rather different flavor. This last one says that if you look at the inverse of the completed matrix, it will have zeros where the original matrix had the unknowns. So I'll give you an example of that in a moment. So lots of good reasons for going for this particular completion. Now in general, finding that completion would be a nonlinear optimization problem for which there are methods applicable, but I want to just show you that you can solve it explicitly in certain cases. I'll just give you one example here. So in this work with Georgescu and Peters, we found that if your matrix has this structure here, 3x3 block structure, and the unknowns, or the unknown entries are all collected together in this block E, assuming A11 is positive definite and hence non-singular, then the optimal E, i.e. the one that gives the maximal determinant completion, is given by this formula in yellow. So it's B transpose A11 inverse C, an explicit formula for this optimal solution. And there are some other patterns for which we can also give a formula like these. So let's see how this works. Let me give an example. So here is a 5x5 matrix with 4 unspecified entries here in this little 2x2 matrix. And the question is, how do I choose those entries? Well, I could just set them to 3/5, because if you think back to that one parameter matrix at the start of the talk with the W parameter, 3/5 is a legal value of W for n is 5. So that would give me a correlation matrix, but it wouldn't necessarily give me the maximum determinant. And I've used the formula on the previous slide to compute the maximum determinant completion. And in fact, it turns out you need to put 9/25 in each of these 4 entries. So with 3/25, or with 3/5, you get 0.087 as the determinant. With the optimal completion, you get 0.124. So as expected, we do indeed get a bigger determinant. What about the inverse of C here? Well, the inverse, as I claimed, has zeros where the original matrix was unknown. So we have this characteristic property of the completion with the zeros in those places. And in fact, that's how we proved the theorem on the previous slide, is by using the fact that we know there must be zeros in the inverse in these places, and then using that to work backwards in a sense and construct the optimal C. So if you'd like to know more, there is a paper, and there's also an article by Dan Georgescu and I in the November 2020 issue of the Actuary magazine. So let me finish with an open problem. And this was posed to me by an actuary a few years ago. So the problem is you have a correlation matrix and you want to round it to a certain number of decimal places, and you want the rounded matrix to be a correlation matrix. And the motivation is that in certain standards you have to specify a correlation matrix, and this would, I guess, appear in a document. So you have to actually write down the matrix to a certain number of decimal places in the document. And in doing so, you want to make sure that what you write down is actually a correlation matrix. So let me just give you an example of why this is non-trivial. So I'm going to generate a random correlation matrix again with eigenvalues 0, 1 and 2. This is done in MATLAB, and we're working here to about 16 decimal digits worth of precision. What I've then done is using the AdvanPix multi-precision toolbox, I've computed the eigenvalues to very high accuracy, to 32 digits, just to check that we actually have a positive smallest eigenvalue. So it's about 2.5 times 10 to the minus 16. So the matrix A sitting on my computer is a correlation matrix. I've then rounded it to single precision, computed the eigenvalues accurately again, and now I find that I have a negative eigenvalue. So just the act of rounding from 16 digits to 8 digits has been enough to perturb that perturb that tiny positive eigenvalue to make it go negative. So rounding can introduce indefiniteness. So what can we do about that? Well, I guess the obvious answer is, well, just now compute the nearest correlation matrix. Okay, we know how to do that by the Newton method or the alternating projections method. The trouble is that will again give me a 16-digit matrix that I now have to round back to, say, 8 digits. And again, in rounding back, I could well lose indefiniteness, lose the definiteness and get a negative eigenvalue. You might have the idea of maybe rounding with rounding in one direction, so rounding all the elements up or rounding them all down off the diagonal. That unfortunately doesn't work. So most of the ideas you might have, which might at first sight seem promising, don't really work. So this problem is actually quite a difficult problem, and it's got a strong combinatorial flavour to it. So I'm not aware of a good way of solving this problem. Hence I've presented it as an open problem, and any progress on this would, I think, be very interesting. So let me conclude. So I found over my many years of working on correlation matrices that they really are a rich source of interesting numerical and algebra problems. We now have very good methods and software for computing the nearest correlation matrix. We know how to do correlation completions, at least in some special cases. In the general case, you'd have to use optimization software. I do want to stress the importance of having numerical reliability. If you derive an algorithm, you really want to be able to prove that it will work and that it will be efficient, because the matrices here, although often small, can be also very large. I've enjoyed partnering with NAG over the years, and now a number of these algorithms are included in the NAG library, where they're used by many companies. And I do have a few extra slides at the end here, which give references if you'd like to see them. The slides are downloadable from this URL, and there's a link here to on my blog to a few blog posts related to correlation matrices where you can find out further information.